Right. Good evening. Actually, the electricity here had went off, and I had to wait until it came back. So luckily, it came back on time. So let everybody join. Okay, then. So people early in the morning, we had started with harmonic oscillators, and I had just given you a small intro on the same. We learned the ground state wave function of the harmonic oscillator, and that is where I think we had stopped. Now we have to start with the energy of harmonic oscillator. Okay. So we have started with. Let me just arrange a few things. Okay. Harmonic oscillator, and in this we have started with 1D harmonic oscillator, also known as you can say linear simple harmonic oscillator. Whatever. So the potential of this is given by people half kx square, and k is basically m omega square. X square. M is the mass of the particular particle, omega is the frequency with which it is oscillating. Then we learned that the differential equation of this differential equation is given by d square psi upon dx square plus 2m upon h square into e minus half m omega square x square psi. This is 0. This was the differential equation. Okay. Then we.
Good evening, sir.
Yes, good evening.
Sir, I have a doubt. Sir, question here.
Okay.
A particle in its first excited state in a finite square wave potential from x is equal to minus L by 2 to x is equal to L by 2.
In finite square wave potential.
From x is equal to minus L by 2 to x is equal to L by 2.
Okay.
Listen,
you have to wait for this. This is symmetric square wave potential. I told you that we have taken unsymmetric square wave potential in the class 0 to L.
Yes, sir. I think minus L by 2 to L by 2 to L हो जाएगा इसलिए
नहीं minus L by 2 to L by 2 but it's symmetric square wave हो गया ना उसकी वजह से because of this v of minus x is equal to v of x now. It's a symmetric square wave. So there's a complete different altogether theory for this. We'll be learning that eventually after harmonic oscillators. Wait.
Okay.
Okay. So, and I told you this about this very clearly when we started with unsymmetric potential. The symmetric potential is different. But okay. So this was a differential equation, and then we learned people the ground state wave function. Then we learned I made you write the formula for the nth state wave function, but I have asked you to not by heart it. Okay. So I just want you to by heart the ground state wave function, which was given by a e raised to minus alpha square x square by 2, where the value of alpha square was m omega upon h square, and we also found out the value of a after normalization. People, I think that came out to be alpha upon 2 pi raised to half, if my memory is correct.
Yes, sir.
Right. Okay. And now we have to proceed from this. Sure. So this is what we learned in the morning, people. Nothing significant here. One thing you need to remember is the wave function which would be used here and there. And only ground state wave function are supposed to by heart. Unlike, see, understand, in 1D box, 2D box, and 3D box, like this. There people we used to identify the wave function of any state. Now, what was a wave function of let's say ground, or like wave function of any state in 1D box? Root of 2 by L sine n pi x 5. So for ground state, it's root of 2 by L sine 1 pi x 5. For first excited, root of 2 by L sine 2 pi x 5. For second excited, root of 2 by L sine 3 pi x 5. And it goes on. So in boxes, people, for us, it was easy to identify the wave function of different excited states. Here in harmonic oscillators, we are not supposed to by heart them. I have already told you because it includes the idea of Bessel functions, people, and Hermite polynomial and everything. So we don't have that in syllabus. Okay. So no wave functions. You can write it. We are not supposed to by heart any wave functions except the ground state wave functions for harmonic oscillator. Okay. So you are just supposed to by heart this one. Next. So what about energy now? Okay. So the hang on. People, nth state energy of this is given by n plus half h squared omega. That's it. Nth state energy of this is given by n plus half h squared omega. Where, listen, n in this case is your quantum number. Just like in 1D, 1D box, n was quantum number, here also n is quantum number. But the difference is that if you remember,
Sir, 0 से start होगा.
Yes, absolutely, and that's what I had meant in the morning also. That we have written psi naught as the ground state, people, not psi 1. In the boxes, we used to write psi 1 as the ground state, we used to write even as the ground energy. Here we have written psi naught, people. Here 0 is valid because when you're making it 0 now, energy is not becoming 0, people. Their energy was becoming 0. See, you are saying the ground state energy 0, which is impossible. Every particle has a ground state energy. There, if you substitute n as 0, energy was becoming 0 now. So n equals to 0 was prohibited that way also. You cannot have 0 ground state energy. So very similarly here, however, if you put n equals to 0, it's fine. So the major difference between the boxes and the harmonic oscillator is that n starts from 0. Okay, so the energy of the ground state, it is just 0 plus half h squared omega, or you can say this is half h squared omega. That's okay. And the best part is, if I ask you energy of first excited state, it's E1, energy of second excited state, it's E2, energy of third excited state, it's E3. It will be 1 plus half h squared omega. Okay, so that's 3 by 2 h squared omega. Then here it will be 2 plus half h squared omega. It will be 5 by 2 h squared omega. Here it will be 3 plus half h squared omega. This will be 7 by 2 h squared omega, and it goes on. And it goes on. Okay, so for nth excited state, energy is En equals to n plus half h squared omega. Then n is what, people? Nth excited state. It's not level, huh? Nth excited state. Here n is not level. In 1D box, n was level B. N equals to 1 was first level, n equals to 2 was second level, n equals to 3 was third level. In 1D box, I repeat, in 1D box, when you wrote, En was n square pi square h square upon 2 ml square. There n was level. What is the difference, people? N equals to 1, that's first level. Okay, ground state. Then n equals to 2 was second level, which was first excited state. N equals to 3 is third level, which is second excited state. However, in 1D harmonic oscillator, people, this is okay. In 1D harmonic oscillator, energy as we just wrote is n plus half h squared omega. And the clearance is that, people, n is not level anymore, n is excited state. N is excited state. So when n is 0, is ground state. You can call it ground state. Okay. Then when you say n is 1, you call it first excited state. When you say n is 2, you call it second excited state. That's the major difference in 1D box and harmonic oscillator. I've tried to ensure that you get a clarity between the difference of the quantum numbers. Make a note, copy please. Just a second. Another shortcut formula which we can take. See, it has been very helpful, For example, in 1D box, any energy was n square E1. In 2D, if you remember, it was n square by 2 E1. In 3D, any energy was n square by 3 E1. So likewise, it's better for us if we convert this into ground state format, like in E0 format. Half h squared omega, that's E0, no? So this is 3 h squared omega. half h squared omega, that's E naught. That's 5 h squared omega. Again, half h squared omega, or what am I writing there?
That E naught I
Sorry, half h squared omega is E naught, so this is 3 E naught. Half h squared omega is E naught, so this is 5 E naught. Half h squared omega is E naught, so this is 7 E naught. Okay, so can we create a general formula here? E1 is 3, E2 is 5, E3 is 7. Can you check a pattern?
2n plus 1.
2n plus 1.
Perfect. 2n plus 1. So you can simply say that En is nothing but 2n plus 1 E naught. Okay, this can be a good time series. Take your time, copy, please. Actually, from here also you're getting that. 2n plus 1 by 2 h squared omega, that's 2n plus 1 half h squared omega, that's 2n plus 1 E naught. So from here also you will get that. Take your time, ask me if you have any questions, don't hesitate, please.
Yes, sir.
Others? Let me know if anybody's writing.
done, sir.
Mention it very clearly and text it. And for clarity also you can write the symbols here. 1D box and 1D harmonic oscillator. And remember, 1D box and 1D harmonic oscillator, both of them are non-degenerate. There is no degeneracy in 1D case. Write it very clearly. In 1D cases, there is no degeneracy. All the eigenfunctions, all the eigen energies, all of them are people non-degenerate. Nobody will be sharing it. Write it. 1D box and 1D harmonic oscillator, both of them are non-degenerate cases. Okay, both are non-degenerate cases. So here we don't have to worry about degeneracy. Okay? So let's take our favorite questions. Okay, shall we? Done, people? Let's
Yes.
write it. Chalo. So suppose again I start with I have given you 7 fermions, and I want us to find the minimum energy state. Okay, let's get started. Then this is only harmonic oscillator. Only harmonic oscillator. Chalo. So we'll start with ground state n equals to 0, then n equals to 1, then n equals to 2, then n equals to 3. I'm not sure how many I require. Let's see. And what about the respective energies, people? So here energy was half h squared omega. Okay, or you can write E naught. Let's start with E naught. Then you have what, if you remember, 2n plus 1 E naught. No? So that's 3 E naught. Then I think we just said odd powers. 1, 3, 5, 7. Odd multiples. Huh? Odd 1, 3, 5, 7. Okay, cool. That's better. No? Why do I remember 2n plus 1? I'm writing this odd E naught. Odd E naught, people. So this 3 E naught, 5 E naught, 7 E naught, 9 plus. Nice. Okay. And I've got 7 fermions, people. You know what to do. 2 will be here, 2 will be here, 2 will be here, 1 will be here. So what's our minimum energy? It's simply I can say 2 electrons are in E naught, 2 fermions are in 3 E naught, 2 more fermions are in 5 E naught, and 2 more fermions are in 7 E naught. So we have got 2 E naught plus, and not 2, sorry, the last is only 1. The last is only 1. Okay. 2 are in E naught, 2 are in 3 naught, 2 are in 5 naught, and 1 is in 7 naught. Total 7 electrons. That's 7 fermions. Okay. So 1 is in 7 naught. So our answer is simply 2 plus 6 plus 10 plus 7 times E naught. Okay. So this is 10, 16, 18, 25. 25 E naught is the answer, or it could also be in the form of, you can write 25 into h squared omega by 2. E naught is half h squared omega. E naught is half h squared omega. So 25 squared omega by 2. Clear? Let me know if you have any questions.
Okay, sir.
Clear, sir.
And what if I give you 7 bosons?
7 E naught.
Write it, please. Okay, 7 bosons. So the answer will be 7 E naught. So that's 7 by 2 h squared omega. If I give you, suppose, 4 spinless fermions, 4 spinless fermions, then what will happen? Minimum energy?
16 in auto.
16 E naught.
16, no? Because 4 spinless means 1 will be here, like one will be here, another will be here, another will be here, another will be here. That's it. When it comes to spinless fermions, only 1 fermion can be in each state. We cannot have 2 fermions, otherwise they become identical people. And 2 identical fermions cannot be in the same state. That's the Pauli's principle. Okay, so that's it. So 1 is in E naught, 1 is in 3 naught, 1 is in 5 naught, and 1 is in 7 naught. Okay, so I can simply say 1 E naught plus 3 E naught plus 5 E naught plus 7 E naught. So it's 7, 12, 15, 16 E naught. So that's 16 h squared omega by 2, which is 8 h squared omega. Okay. Let me know if you have any questions. You know, in this, a good ratio problem could also be asked. Like I can ask you, in numerical answer type only, what is the ratio of occupant? What is the ratio of the minimum energy of 7 bosons to minimum energy of 4 spinless fermions? Something like that. So ratio could also be asked. So you have to calculate 7 by 2 h squared omega. You have to divide it by 8 h squared omega. Okay, if ratio is asked, something like that. So h squared omega gets cancelled. You get 7 by 16. That will be your answer. Then you have to calculate this using calculator. You write it until 1, 2 decimal, whatever you have asked in the question. Okay. So that's also there. MSQ could also be asked. Okay. So there could be options: fermions, bosons, spinless fermions, and then fourth would be probably repetitive. It has to be either of the 3, but you may not use the word fermions. So like they might write protons. So protons are, for example, fermions. Okay, something like that. So for that, we need to know the standard, like a standard. No, I don't know what do you call it. Standard atomic model. No. The elemental particle table. So that we need to know. Okay. Okay. Standard model basically. Chalo, next. So that's about our 1D harmonic oscillators. Okay. Now let's learn. Oh wait, before that. So here's another question. So they have given us wave function, which is 1 by root 3 psi naught plus 1 by root 3 psi 1 plus 1 by root 3 psi 2. Okay. And hang on. And they have mentioned we have got 3 fermions. Okay. And they're asking us minimum energy of the system is and maximum energy possible of the system is. Okay. Again, this is a question for 1D harmonic oscillator. So suppose they have given you wave function of a particle, and that wave function is made up of psi naught, psi 1, and psi 2. It means psi naught will have a respective eigenvalue E naught, psi 1 will have a respective eigenvalue E1, and psi 2 will have a respective eigenvalue E2. All of them are equally probable. All of them are equally probable. 1 by root 3, 1 by root 3, 1 by root 3. Now, if you just write, so what are the possible energies? E naught is a possible energy, E1 is a possible energy, and E2 is a possible energy. We know the value of E naught, by the way. E naught is, or you can just write E naught, E1 is actually 3 E naught, and E2 is actually 5 E. So that's also fine. So minimum energy, we obviously know when it comes to minimum, 2 electrons will be here and 1 will be here, and we are done. So 2 will be in the ground state, and 1 will be in the this E1 state, people, and 1 will be in the E1 state. So 2 E naught plus E1 is nothing but 3 E naught. E1 is nothing but 3 naught. So this is 5 E naught. So this is done. E minimum of the system is done. The interesting is the maximum one, people. So obviously you have to start in reverse order when you say maximum. Maximum means now you have to start from here. 2 electrons have occupied the maximum state, and then 1 electron will occupy the second state. You have to start in reverse order. That's the meaning of maximum. So in that case, what will happen? 2 electrons will be in the E2 state, and 1 electron will be in the E1 state. I hope you understand. Because reverse. That's the meaning of maximum. That's it. No? But remember, the thing is, for maximum actually can go until infinity. You can have E3, you can have E4, you can have E5, it can go until infinity. But the question is, it has been clearly given that the only possible energies you can occupy are E naught, E1, E2. The only possible energies we can occupy are E naught, E1, that has been clearly given to us. And hence, now maximum has a limitation. What is the maximum limitation? 2 electrons will be E2 and 1 electron will be in E1. I hope that's understood. Okay. So this is 2 into 5 E naught plus 1 into 3 E naught. So this is 2 5s are 10, 10 plus 3, that's 13, 13 E naught E2. Tell me if you have any questions, don't hesitate. Make a note.
So can you please go through the part where you said that we have concluded that only E naught, E1, E2 are the possible energy states?
No, because wave function is given to us now, and wave function is linear combination of psi naught, psi 1, and psi 2. So psi naught can have only eigenvalue E naught. Psi 1 is the wave function corresponding to E1, psi 2 is the wave function corresponding to E2. Do I have infinite wave function combination here? No, no. So the only possible energies that I can have is either E naught or E1 or E2. I cannot have anything beyond that. No? That's it. These are the only possible states. Okay. Yes. Clear?
Yes, sir.
So basically, the wave function, whatever is the particle which is right now traveling, the wave function that is associated with it, it has a maximum capability. When you say a yellow color, like I said, it is actually the mean color. When you say white color, white is made up of the 7 colors that we are going to speak about. So very similarly, the wave function here, it is made up of only these 3 kind of energies or these 3 kind of wave functions. In a combination of these 3, it cannot go beyond this. It cannot go beyond this. So this is the limitation. This is the boundary. You cannot have EP for this time. Okay, people. Chalo, let me try it.
So please wait.
Take your time.
Sir, these are known as orthonormal basis, no?
They are supposed to be orthonormal. Always the eigenvalues and eigenvectors, they are supposed to be orthonormal. Yes. The eigenvectors corresponding to the eigenvalues, they are supposed to be orthonormal. So you can always write that, psi naught, psi 1 is basically 0, but the value of psi naught, that will be 1. Yes. Let me look at your question. The plastic bottle makes weird sound. The other day, I was seeing these kids who were like in the society riding the bicycles. So some of them discovered something which even you must have seen or did in your childhood. So just an empty plastic bottle, they put it in the back of the seat above the tire, and it creates a sound as if a good bike with a good what do you call it? A silencer is running, like boom, boom, that kind of a sound. So basically, the bicycle that you have, okay, like something like this. So here, below the bicycle, there is this kind of gap now. So here there is a space. If you fit a bottle here, like whatever open bottle, but like whatever, however you draw the bottle, but you need to draw an open bottle. Or just keep an open bottle here. It will behave as if it's a silencer and it will create sound as soon as the bicycle is riding. So the kids in the society were doing this yesterday. Okay. Anyway, chalo, done. Let me know.
If you write it now.
Yes, sir, done.
Okay, chalo, next. So now let's start with 2D harmonic oscillator. Okay. Again, people, we are not supposed to by heart. We are not supposed to by heart any of the wave functions. In this, not even ground state wave function this time. No ground state wave function, no wave function. If at all they want you to play with wave function, yeah, they have to give you. So suppose they might give you, like A into some function, and they might ask you to find the value of A, normalization. Otherwise, you don't have to by heart any wave function. The rest we are aware what we are supposed to do. What about energy, people? It will be now a function of nx and y. But energy is a scalar quantity, so it will be E nx plus E ny. What is energy, people? N plus half h squared omega. So n plus half h squared omega. Again, energy would be what? N plus half h squared omega. But since I've got nx and y, this quantum number is nx, this quantum number is ny. However, listen to this now very carefully. This is fine. We can stop here. But who told you that omega will be same as well? What is omega? Omega is angular frequency. Now, who told you frequency along x and frequency along y will be same? It's not necessary. So people, when behavior in all the direction is same, what is the physics term that we use or English or whatever?
Isotropic.
Isotropic. Correct. So when if omega x and omega y are equal, right now you can write omega x and omega y. If they're equal, then you call it isotropic 2D harmonic oscillator, people, which is the standard one, which is written in all the books. But they don't use the word isotropic. They started 2D harmonic oscillator. And assume that omegas are equal. No, people, you cannot assume that they are equal. They become isotropic harmonic oscillator. So right now I want you to write like when you are writing. Okay, we will make it. We'll keep this nx, we'll keep this ny, keep it omega x and omega y as of now. Okay, and we will right now call it an isotropic 2D harmonic oscillator. An isotropic 2D harmonic oscillator. However, what we need to learn is isotropic only. So we'll just mention that now. So for isotropic harmonic oscillator, 2D harmonic oscillator. Okay, the value of omega x and omega y, the frequency along x-axis and along y-axis of the particle, it will be same. Let's call it omega b. In that case, of energy nx and y, that will be what? It will be nx plus half h squared omega plus ny plus half h squared omega. Make a note. And once we complete 2D and 3D now, I will take a couple of good problems related to anisotropic harmonic oscillators asked in the net JRF papers. I'm not sure if you have asked anisotropic harmonic oscillators in JAM or not, but we'll still take a couple of good questions on this because year by year the level of JAM, like kind of questions in JAM have been increasing, and anyway they are also running out of type of questions. So they might just ask the question on anisotropic as well. So take it at the very end. हाँ बोलो.
सर यहाँ पर जो एनर्जी है वो भी nth excited state के लिए या फिर लेवल के लिए कौन से क्या है?
No, right now,
Energy
right now just NX and Y, no? So just like you used to write 1, 1, 1, 2, so that we have
No,
figured out.
energy of the अच्छा कुछ okay.
हाँ,
It
right now
depends
it
upon that NX and Y.
will depend on NX and Y, yes. Right now तो it's ठीक है. So when you say isotropic, it means behavior is same in all the directions. When you say behavior, as in physical behavior, like frequency of vibration, it should be same in all the directions, x axis and y axis. So you say omega x and omega y will be equal, they become omega. ठीक है. Should I go to the next page? Let me try. Next.
Just a minute.
Okay, sure. Take your time.
Yes, sir.
Sure. So energy nx and y, next comma and y, this is given by, let's take h squared omega common people. So we will be left with nx plus half and y plus half. And we have taken h squared omega common. So what do we have? Nx plus ny. Half plus half is 1 h squared omega. And now we will say let nx plus ny be n. But people, okay, no, not but n here is still a quantum number starting from 0. I repeat. Unlike boxes where n was just a random number, here n is not a random number. N here is still a quantum number starting from 0, 1, 2, 3. Okay, it's not a random number. You will realize why. Why? Because nx and y starts from 0 now. If it starts from 0, people, what are the possible combinations you can always have? 0, 1, 2, 3, 4. Don't you think while adding will have all the possible combinations? Do you have square this time? There's no square now. So don't you think we'll get all the integers this time? If you take any combination of nx and ny, this time while adding, you will get all the integers. You can get 0, you can get 1, 2, 3, 4, 5. You'll get all the integers this time. Last time we couldn't get it, because we had nx square plus ny square was n square. Because of this, we couldn't get all the integers. We started from 1, 1, but then this became 2, n square was 2, and n was root 2. And hence, there n was a random number. But here this time n will be an integer people starting from 0. Okay. So anyway, so nx plus ny is n. So the energy of nx and y for 2D harmonic oscillator is n plus 1 h squared omega. Okay, make a note. I hope you are understanding this. Remember, nx and ny also start from 0 to 1. All of them are 0 to 1. Nx will also start from 0 to 1, like 0, 1 to 3. And y will also go from 0, 1 to 3. They are any quantum numbers, but n will also be a quantum number this time, people. Okay. So the ground state will be when n is 0. First excited will be when n is 1. Second excited will be when n is 2. So that idea is not changing in harmonic oscillator. That's better. That's less confusing this time. You know? So the ground state will remain E0, people. Okay. The first excited will remain E1. Okay. The second excited will remain E2. So you can also say for pth excited state, generally, like for pth excited state, the value of EP would be just p plus 1 h squared omega. And what is the ground state value, by the way? We did not discuss the ground state value. The ground will given both of them are 0, 0. Nx and ny, both of them are 0. Yes, just h squared omega. Okay. So for ground state, both nx and ny would be 0, 0 people. Nx and ny both would be 0. So in that case, your value of E0 would be 0 plus 0, that's 0, and 0 plus 1 h squared omega, that's just h squared omega people. I hope you are understanding. Let me know if not. ठीक है, shall we? Energy is just n plus 1 h squared omega. Chalo, let me try it. Next, now we'll do the table part of it, because this time degeneration exists. Huh? So let's start, for example, state. Then we will write the value of n. Let's start from n. And how can we write nx and y? That will be discussed. We'll write the respective en, and we'll write degeneration. Okay. So let's start with the ground state. N should be 0. Nx and y will also be 0, 0. Okay. N is basically nx plus ny. Okay. En, that's actually n plus 1 h squared omega. Okay. So n is 0. I think you may not be comfortable with what do you say, this way. I feel nx and y will write it first, so that you go from left to right. But I will still start from 0 here. How can I get 0 when nx and ny both are 0? Nx plus ny both are 0. And the value of E0, this will be 0 plus 1 h squared omega, that's just h squared omega. Nobody else can give me this value. Degeneracy is 1, or you can say no degenerate. 1 for degenerate, or you can say non-degenerate, whatever. Next, first excited state. Value of n will be 1 people. Now the best part here is, like I said, pth excited state, n is p. First excited state, n is 1. How can I get 1?
0, 1, 1, 0.
0, 1, and 1, 0. So E1 is 1 plus 1 h squared omega, 2 h squared omega. The degeneracy is 2. Clear? Next, let's talk about second excited state. Second excited state, n will be 2. How can I get 2?
1, 1.
And 1.
And
2, 0.
2 0
and
2, 0.
0, 2.
0 2.
Bas, okay. Okay. So we have 1 1 2 0 and 0 2. Okay. So the value of E2, that's actually 2 plus 1 h squared omega, n plus 1 h squared omega, 2 plus 1 h squared omega, that's 3 h squared omega. And degeneracy is 3. Don't you think we're getting good pattern here? Let's see. Third excited state. 3. How can I get 3?
1, 2, 2, 1.
2, 1,
2 2 1
3, 0, 0, 3.
0 3 3 0. That's it.
4 is
So yes, we have a degeneracy is 4, and we have got that E3 is n plus 1 h squared omega, that's 3 plus 1 h squared omega, that's 4 h squared omega. And now you know what to do. You can generalize this. Degeneracy also has a formula this time. What could get better, people? Even degeneracy has a formula this time. Make it, please.
N plus 1.
That's it. Actually, degeneracy is standardly denoted by G, letter G. So degeneracy of n state, you write Gn. So here the value of G1 is 1, the value of G2 is 2, the value of G3 is 3. That's actually funny. G4 is 4, G2 will be whatever. Oh no, not 1. We'll write G0 here. That's best now. G0 is 1, G1 is 2, G2 is 3. Let's call this G3 is 4. 0 is for ground state. Or you can just write G. You don't have to write G. Just keep it Gn. ask me if you
सर
बोलो।
1D ऑसिलेटर में जैसे लिखते हैं psi 11 psi 1 को यहाँ
हाँ
किसी
यहाँ पे
तरह
लिखिए
लिख
ना,
देना।
हाँ यस यस, सो वेव फंक्शन जैसे यहाँ पर आएगा psi 0 0, here the wave function could be psi 01 psi 10, here the wave function possibilities are psi 11 psi 20 psi 02, here the wave function possibility will be psi 12 psi 21 psi 03 psi 30, absolutely. I said just asking randomly. Usually all these wave functions are equally probable. So if I tell you, suppose, let's talk about third excited state. If I tell you probability of all the wave functions, like probability of having any of the eigenvalue, okay, like eigenvalue is same for all of them, but probability that the particle will be in any of these four states is the same, then what is the individual probability?
0.25.
0.25.
0.25. That's basically 1 by 4. That's understood. Now 1 by n. That should be the answer. Here it will be 1 by 3, 1 by 3, 1 by 3. Here it will be 1 by 2, 1 by 2. Here it's 1. Here it will be 1 by 4, 1 by 4, 1 by 4, 1 by 4. They all will be equally probable. This theorem is also known as it used to have a name, I think, equal a priori probability theorem, something like that. It's called a priori. I remember that word. This word they used to use. A priori. Okay. So equal a priori probability theorem, something like that. So basically all these states are equally probable. All of them. It's not that one of them is more probable and one of them is less probable. No. All of them will have same probability. So I'll just create a question from this time. I'll first copy this. Let's complete this. Okay, people, have you written this? Should I go to the next page?
Yes, sir.
Okay. So we have got for nth excited state. For nth excited state, the value of this nx, ny, we don't care. But the value of n. First excited is 1, second excited is 2, third excited state is 3, and nth excited state has value n itself, people. Now En, that's n plus 1 squared omega. That's fine. Okay. And the value of degeneracy, as you clearly see, people, 0 is 1, 1 is 2, 2 is 3, 3 is 4. So n will be n plus 1. Okay. G will be n plus 1. That's the degeneracy of nth excited state. Degeneracy of nth excited state. Okay. Good. So let's just talk about that equal a priori theory, probability theory, something like that exists. But the crux of that, what do you say, theorem is that each state sharing same eigenvalue is equally probable. It's not that basically one is more probable, other is less probable. No. So for example, okay, if we talk about third excited state, okay, it has got how many wave functions? It has got 4 wave functions, right? The wave functions are psi 12, psi 21, psi 30, psi 03. Okay, all of them are equally probable. So probability that a particle will exist in psi 12 is equal to probability that a particle will exist in psi 21 is equal to probability that a particle will exist in psi 30 is equal to the probability that a particle will exist in psi 03. Everything is equally probable. But remember the states sharing the same eigenvalue. All of them are equally probable. And total probability should be 1, people. Okay, so you can also say, so you can call them P. You can just call them P. Say. So the value of P plus P plus P plus P, the total probability should be 1. Okay, so 4 times P will be 1. So P will be 1 by 4. So probability that the particle will exist in each state is 1 by 4 or 0.5. Okay, probability that particle will exist in either of the state. Particle will exist in either of the state is simply 1 by 4 or you can say 0.25. Copy. Ask me if you have any questions. Then people should I go to the next page? Copy, please. Probability that the particle will exist in either of the state in this example is 1 by 4 or 0.25.
The previous slide.
Sure.
One by n plus 1 can say
Done, sir.
probability.
Probability
In excited state.
Perfect. Yes, third excited state has got 1 by 4 now. So you can call it 1 by n plus 1. So you all have learned how to generalize. Shall we done, people? Next. Let's take a question. Here we go. So again, suppose I'm giving you 9 fermions. Okay, and we have a 2D isotropic harmonic oscillator. Okay, and I want to find the minimum energy of the system. Okay, let's work on this. This time degeneracy exists, so be very careful. Okay. Okay, so let's start with n equals to 0. Remember n is nx plus ny. So I can get this only in 0 0 combination. So I have 2 electrons here. Then if I talk about n equals to 1, I can get 1 as 1 0 combination and 0 1 combination. I have 2 more electrons here, 2 more electrons here. Then let's talk about n equals to 2. I can get 2 as 2 0 combination. I can get as 0 2 combination. I can also get it as 1 1 combination. So 2 3 4 5 6 7 8 and 9. Okay. And somebody had taught me a bit chemistry yesterday. So if I thought if you want, you can write all the 3 here, but it is not going to affect our energy, people. Okay. So if you want, you can fill the 3 states first, and then you can come back and fill the half state. But it won't affect our energy. Okay. So up down, I'm writing this step. Okay. So that's it. What's our answer there? And how about energy? Do we have a shortcut formula this time? Did we learn any shortcut formula for 2D for energy? I said n plus 1 squared omega anyway, but hang on. So I'm only thinking it's still E naught is h squared, then 2 h squared, 3 h squared, 4 h squared. It's still the same, no? H squared, 2 h squared, 3 h squared, 4 h squared. Okay. So I can directly write h squared omega, then 2 h squared omega, then 3 h squared omega. Okay. So basically it's n plus 1 h squared omega. That's the only formula. But how shortcut? I mean, it cannot be simplified further than that. No? En is just n plus 1 h squared omega. That is obvious. Okay. Okay. No, I was thinking should we write it in terms of E naught or not? But what is E naught? E naught is h squared omega. If you want to write this in terms of E naught, people have a look. What is En? En is n plus 1 h cut omega. So what is ground state? That's 0 plus 1 h cut omega. So that's just h cut omega. Okay. And if you talk about En, so that's n plus 1. H cut omega is actually E naught. So En is n plus 1 E naught. Just in case if you want to write it in terms of E naught. Otherwise, you can write everything in terms of h cut omega also. En is n plus 1 h cut omega. N plus 1 E naught. En is n plus 1 E naught. You can write this above margin. En is n plus 1 E naught. Okay. So here you have got E naught. Then I have got 1 plus 1, that's 2 E naught. Then I've got 3 E naught, and it goes up. That's it. So answer, the minimum energy is 2 electrons are in the ground state, then 4 electrons people are in the first excited state, and then 3 electrons are in the second excited state. 4 in the first excited, okay, and 3 in the second excited. So answer is 2 plus 8 plus 9 into E naught. So that's 19 times E naught people. I hope you understood this. Tell me if not. Don't hesitate. Take care.
Yes, sir.
Now you can predict what will be my next question.
Boson.
Okay, good. So write it please. Time goes on. Answer will be 9 E naught. So that's 9 h cut omega. Okay. So this is 19 h cut omega. 19 h cut omega. E naught is h cut omega this time. For 1D it was half h cut omega. For 2D it is just h cut omega. Okay.
3 to 3 h cut omega. 3 by 2 h cut omega.
3 by 2 h cut. You have to get that. Yes. So 9 bosons. Answer will be 9 E naught. Okay. 9 bosons. Same question. Answer will be 9 E naught, or you can write 9 h cut omega. So let's try for 9 spinless fermions people. Okay. So again I will just draw the table. Where is spinless fermions? Okay. So let's do that. We have got n equals to 0, then we have got n equals to 1, then I have got n equals to 2, and then I have got n equals to 3. N is nx plus ny. I need to remember that. So nx plus ny, 0, 0 will give me 0, 0, 1 is going to give me 1, and 1, 0 is going to give me 1. 0, 2 will give me 2, 2, 0 will give me 2, 1, 1 will give me 2, then 0, 3 will give me 3, 3, 0 will give me 3, 1, 2 will give me 3, and 2, 1 will also give me 3. Okay. And remember the degeneracy, by the way. 1 degeneracy, 2 degeneracy, 3 degeneracy, 4 degeneracy. Here, even if you don't write this now, if you just remember degeneracy, then also fine. You don't have to, write this in exam. If you remember what is degeneracy, you can just write G1. Here you write G1, G2. Here you write G1, G2, G3. Why do you want to write all the states also? The writing state is not going to be helpful. Now you already know the degeneracy, and very easy to determine. Okay. So you don't have to write all the states. Okay. Time saving stuff, people. I'm just telling you. Okay. You can directly write degeneracy. Okay. Anyway, so 9 spinless fermions, I cannot have 2 electrons in the same state, otherwise they'll be identical. So 1 in each. 1 here, 1 here, 1 here. 3 is done. 4, 5, 6, and then 7, 8, 9. That's it. So the minimum energy of the system is 1 is in the ground state, 2 is in the second state, E1. Okay. 3 electrons are in E2 and 4 electrons are in E3. Okay. Okay. So 1 E naught plus 2 into E1 is actually 2 E naught. Okay. E2 is actually 3 E naught, and E3 is actually 4 E naught, because En is n plus 1 E naught. En is n plus 1 E naught. Okay. So I'll just take that later. So answer of E minimum would be, I can take E naught common. I'm left with 1 plus 4 plus 9 plus 16. So that's 16, 25, 29, 30. 30 E naught people, or I can say 30 h cut omega. I hope you got this. Tell me if not.
Sir, 16 की जगह 12 आएगा. 3 into 4
26
E
होगा
naught.
sir. 26
हाँ,
होगा.
sir.
I did mistakes.
Sir,
He is
3
asking
into
for
correct दिया.
अच्छा,
Four
okay, okay,
is
अच्छा, खुशी खुशी में 1 2 3 4 का जा रहा हूं मैं. Okay, I have only 3 electrons here. Right, I don't have 4 electrons. Okay. इतनी खुशी अच्छी नहीं है. इतनी खुशी अच्छी नहीं
मैंने
है.
जानबूझ के किया था ना.
I wish. But
हो गया वो.
सही है. But yes, such happiness. Like we are so much used to and with the patterns now. But okay, no excuses. Mistakes happens. So 4 is that 12. So our answer will be 26. Okay, good. So exam, when our favorite question comes, don't be like me. Okay. Keep patience and ensure that you get the mark there. Don't rush. I remember screwing up, a simple question on complex number. There was a graphical question, and I was like, this question is so easy. But I remember doing up a very silly mistake there, and it was for 1 mark only, but still I lost that 1 mark. I still have that in my head. And then I told you some examples, like for example, the Clausius Laplace stuff also, where instead of substituting Kelvin, I ended up substituting Celsius. Keep on in the exam, people. Okay. And please practice as many mock tests as possible. That's important. Shall we done? Next. So let's now take 3D harmonic oscillator. Okay. I believe the fact that even if I don't teach you 3D harmonic, you guys can now create your own 3D harmonic.
Yes sir.
Yes, sir. NX plus NY plus NZ.
Good. All I have to give you is 20-15 minutes, and you will also do your create your questions also. So, we're saying that 3D harmonic oscillator. So let's start with En people. That's I can say now it's a function of Nx. By the way, here also we'll have isotropic and anisotropic. We'll write down anisotropy first. So Enx, Eny, Enz. That should be Enx plus Eny plus Enz. So this is Nx plus half h cut omega plus Ny plus half h cut omega plus Nz plus half h cut omega. Okay, and nobody told us that omega will be equal first of all, and I've substituted bracket at the wrong place. Okay, so omega y and omega z. So right now this is anisotropic. Basically behavior is not same. Isotropic. Okay. So for isotropic 3D harmonic oscillator, okay, the value of energy Enx, Ny, Nz, that would be, when you say isotropic, it means frequency of vibration will be same in all the directions. Let's call it omega. Say it's omega. So you can take h cut omega common this time. So if you take h cut omega common, you'll be left with Nx plus Ny plus Nz plus half plus half plus half. What do we have, people? Nx plus Ny plus Nz. Yes, half of half. That's 3/2. Copy.
Yes, sir.
So कौन कह रहा था quantum difficulty बताओ जरा.
सर अब तो बहुत आसान लग रही है.
Good. Okay. So what do we have? People En. So now I'll just write substitution. Let n be equal to nx plus ny plus nz. Again, people see nx, ny, nz. All of them are quantum. N will also be quantum because all of them are allowed to have zero values this time. Because even if you substitute zero, people, energy is not becoming zero. You are having a ground state energy. Even if all the quantum are zero, what will you have? You will have 3/2 h², and hence n will also start from zero. All of them start from zero this time. So again, the best part about harmonic oscillators is, we don't have to scratch our head when it comes to ground state, first excited state. Again, the story remains same. Like n equals to 0 is ground, 1 is first excited, 2 is second excited, 3 is third excited. So that remains same. Anyway, so the value of energy would be now nx plus ny plus nz, that's n plus 3/2 h², okay? N plus 3/2 h². And energy of the ground state, people, E naught, that's 0 plus 3/2, so that's just 3/2 h². Just small diversion. I wanted to discuss this since long. The dimension of wave function. A small diversion before I forget again. So ground state wave function is right now for this 3 harmonic is c/2 h². Okay. Before we take question on this, just a small diversion here. People, for 1D box, for an example, for 1D world, I'm taking 1D box as an example. The wave function is actually root of 2/L sine n pi x by L. This does not have any dimension. Length gets cancelled. X is length, okay? X is position. So length gets cancelled, meter gets cancelled, no dimension whatsoever for sine. But 2 does not have a dimension, but length has a dimension now. That's unit is 1 upon meter is there. Okay. So here, if you want to write the unit is actually root of 1 by meter, people. Or you can say 1 upon root meter, or you can say 1 upon meter raised to half, or you can say meter raised to minus half. This is the dimension of the wave function in 1D. Meter raised to minus half. So unit of wave function in 1D, the dimension would be length raised to minus half. Mass is 0, length is minus half, and time is 0. But this is only 1D world. Copy this first. This is not a part of the ongoing topic, but I wanted to discuss this, so we are taking this. In one of the IISc papers, they have asked this question. Dimension of the wave function, I think it's 3D. That was the question probably. Okay. 2D box. Okay. So in 2D world, people, when we write sine nx and y, we have actually 2/L into sine nx by x by L, and then sine ny pi y by L. If you remember root of 2/L, that actually becomes 2/L there. So this again does not have any dimension. This does not have any dimension. It's a sine trigonometric term, people, but this has a dimension. The unit is just 1 upon meter this time, people. Or you can say just meter inverse. So the dimension of the wave function, it is just, there is no mass, there is length minus 1, and there is no time. Now the dimension is changed. In 2D world, the wave function has dimension meter is to minus 1. But in 1D, it was meter is to minus half. And here it is meter is to minus 1. Okay. And similarly, in 3D, what will be the answer, people?
Minus 3/2.
Minus 3/2.
Yes, okay. So minus half, minus 1. You have meter is to minus 3/2. That will be the unit. And dimension will be length is to minus 3/2. M0, L, minus 3/2, T0. Okay, people. Chalo. Let's go back to our harmonic oscillator, 3D harmonic oscillator, but isotropic. Okay. So I want us to again create table. Let's work on the table. 3D harmonic oscillator, isotropic. So let's start with state. Then again the values of nx, ny, nz respectively, and the value of n, and then the value of en, and then the value of dz. So en is this time n plus 3/2 into h². Okay. So to start with ground state, the ground state value of n will be 0. So the value of E0 will be 0 plus 3/2. That's 3/2 h². How excited can I 0 and all of them are 0. That's it. It's a non-degenerate state. Degenerate is only 1. Let's talk about first excited state. Okay. So the value of E1 will be like n is 1. Quantum number is 1. First excited state. Remember, pth excited state, quantum number is p. Again, that's the best part about all the harmonic oscillators. Okay. There is no confusion here. So pth excited state, the value of n is p simply. Anyway, so 1 plus 3/2, that's 5/2 h². Okay. Now how can I get 1, people?
1 0 0 0 1 0 0 0.
Perfect. 1 0 0 0 1 0 and 0 0 1. So we've got threefold degeneracy. Threefold degeneracy. Okay. Next. Let's talk about second excited state. So value of n will be 2. E2 will be 2 plus 3/2. That's 7/2 h². Okay. How can I get 2 now?
1 1 0
Let's start with 0 0 2. Then 0 2 0 and 2 0 0. That's 1. And then like you said, 1 1 0. That's there. Then people 1, like you can also write 0 1 1, and you can also write 1 0 1. 6 possibilities. 0 0 2 0 2 0 2 0 0, and then 1 1 0 0 1 1 and 1 0 1. Or however you're comfortable writing this. If you're comfortable with 1 1 0, then 1 0 1 and then 0 1. However you're comfortable writing this. Okay. So we have got 6 degeneracy people this time. This time we have got 6 degeneracy. Any questions? Anyone? Any pair? Shall we?
Yes, sir.
Third excited state. The value of n will be 3. The value of En, which is E3, this will be 3 plus 3/2. That's 6 plus 3/2, which is 9/2 h². Now we have to take care and understand how do we write 3 people. So one is 3 0 0 0 3 0 0 0 3. One combination done. Another possible pair. There is only noise actually. I cannot hear anything. But 0 1 2 people. 1 2 can give me 3. 1 2 can give me 3. But 0 1 2. How many degeneracy this has?
3.
Nahi na.
6.
6. Yesterday only I taught you this. When all are different, there are 6 possibilities. Okay. So 0 1 2 0 2 1. Okay. Then 1 0 2, then 1 2 0, and then 2 1 0, and then 2 0 1 people. Okay, so 0, 1, 2, you keep 0 fixed and just shuffle it 1, 1. Similarly, keep 1 fixed, shuffle 0 and 2, and keep 2 fixed and shuffle 1 and 2. So this further helps 6. Can you tell me another possible pair?
1, 1, 1.
1, 1, 1.
Yes, 1, 1, 1. So in total, I have 10 these in the sequence. 10. By any chance, are you aware of this? It's a very popular series, no? This number 1, 3, 6, 10. We have 1, 3, 6, and 10 as these are the sequence. Are you aware of this formula? When do you get 1, 3, 6, 10?
And n into n plus 1 by 2.
I'm not 100% sure. Maybe. Let's check. G. So if I start it down, then 0 plus 1 by 2. No. N is 0, no? But remember, our n is 0. So don't write n into n plus 1. Our n is 0. You write n into n plus 1 when n is 1. So you have to make a small manipulation. This is correct.
n plus 2 हो जाएगा. n plus 2 हो जाएगा.
N plus 1 into n plus 2 by 2.
Yes, sir.
Total manipulation, yes. So, but guess is correct. Have you understood, people? So the guess that he made, that's correct actually, but provided that n starts from 1, then answer is correct. But our n starts from 0. So in that case, we have to make a small manipulation here, and that is n plus 1 into n plus 2 by 2. And now our answer will be correct. Because when you substitute 0, check, you will get 1 people. Substitute 1, you will get 3. Substitute 2, you will get 6. Substitute 3, you will get 10. I'll substitute 3 and check. Let's check for G3. So 3 plus 1 into 3 plus 2 by 2, which is 4 into 5 by 2, which is 2 into 5, and that is 10 people. G3 is 10 as expected. For third excited state, degeneracy is 10 people. Yeah. Make note. This is the formula for degeneracy for 3D harmonic oscillator. N starts from 0. Mention it very clearly. So 1, 3, 6, 10 is a popular series. You can remember n into n plus 1 by 2, but n should start from 1 in that case. If n is starting from 0, then you have to make a manipulation. N plus 1, n plus 2 by 2. Okay. Any questions? Anyone? Shall we? Let me try it.
Yes, sir.
Okay. So before I proceed, so there is an interesting formula. Somebody had come up with this on the internet, some explorer. So I was just looking for something and I found this. See, 1D is non-degenerate, you already know. Okay. For 2D, the value of degeneracy, people, that was n plus 1, just n plus 1. Now, for 3D, the value of degeneracy, we learned it is n plus 1 into n plus 2 by 2. Remember, n starts from 0. Don't forget that. Okay. So he said, if we ever want to expand this idea to pth harmonic oscillator, anyway, three dimension is done. But just in case, if we want to discuss this idea for p-dimensional harmonic oscillator, he came up with a very beautiful theorem there, a whole proof. Three-dimensional harmonic oscillator. So he also has a published paper on this actually, harmonic oscillator. So people do these time passes. We don't know what will be the use of this in future, but people has kept their theory ready. If something like this exists, we shouldn't feel like that we don't know anything about it. So for three-dimensional harmonic oscillator, the value of degeneracy, people, he said it will be n plus p minus 1, the whole factorial upon n factorial into p minus 1 factorial. Outstanding work. The paper is published on this. It's not available in the books. It's the work of 21st century. This is a student from some college. He worked on this out of curiosity. So remember, when you are in PhD, when you are a student or researcher, it's not necessary to always do things which you think already exist. Do whatever which may exist. Just like people have got theory ready for monopoles. Even though monopoles don't exist, but we still have theory ready. Just like Einstein had kept ready the theory for gravitational waves 100 years ago. But gravitational waves were discovered just 5, 6, 7 years ago. People. I think 2014 probably, right? 7 years ago. So keep the theory ready for whatever thing that might be interesting to you. Okay, so we can check this formula. The most complicated one is 3D. Let's check for 3D. Let's substitute n is 3. I'll be getting this one. Okay, like for 3D basically. For 3D. So the value of p will be 3. Because p-dimensional, no? So 1 dimensional, 2 dimensional, 3 dimensional, 3 dimensional means p is 3. Okay, substitute. What is Gn? Gn is n plus 3 minus 1 factorial, the whole upon n factorial into p minus 1. So that's 3 minus 1 factorial. So what are we getting? N plus 2 factorial upon n factorial into 2 factorial. N plus 2 factorial, I can write n plus 2 factorial as n plus 2 into n plus 1 upon, are you going correct?
Into n factorial.
Into n factorial, and then I have n factorial, 2 factorial. So it's n factorial, n factorial gets cancelled. We got n plus 1, n plus 2 by 2. 2 factorial is 2. Nice, no? Make a note. Okay. Sure. Let's take next question. Let me know if you're writing. Shall we? Take it. Here we go. So let's again take our question where I'm giving you 15 fermions, 15 bosons, and 15 spinless fermions. Okay. And suppose I'm giving you the value of energy minimum for this is, let's say, and let's call it, just something. Let's say EA or EF. Let's say the energy minimum system for this is, let's call this EB, and let's say energy of the spinless fermions, let's call it ES. So suppose the question is related like what is the ratio of EF to EB is to ES, and there could be 4 options. Okay, let's work on this. So 15 fermions, people. Let's have fun. Okay, so what do we have to start with? N equals to 0, 0, 0, 0. That's it. 2 electrons will be here. Then N equals to 1. 0, 0, 1 is possibility, 0, 1, 0 is possibility, 1, 0, 0 is possibility, and I have a 2 more, 2 more, and 2 more. 8 are done. Okay. Then N equals to 2. 1, 3, and then now we have 6. By the way, listen, there is no need to write the states. You remember 1, 3, 6, 10. No? So 1 degeneracy, okay, 3 degeneracy. Now I will have 6 degeneracy. So 1, 2, I will just write 1, 2, 3, 4, 5, 6. 6 degeneracy. No? You don't need to write the states. What is the need? To like of wasting our time in writing the states. If we know the degeneracy already, so we know the degeneracy better. If you want to write the states, then obviously we know the answer. 0, 0, 2, 0, 2, 0, 2, 0, 0. That's one possibility. Then 0, 1, 1, 1, 0, 1, and then 1, 1, 0. So there's no need to write the states. That's what I'm saying here. Anyway, so I've got already 2, 4, 6, 8. Total are 15 now. So 9, 10, 11, 12, 13, 14, and 15. Thus, done. So our answer for the first case, the value of EF would be, okay, 2 electrons are in the ground state, then 6 electrons are in the first excited state, and the remaining 7 electrons are in the second excited state, people. But we have not created a general format in terms of E naught, because doing that helps us. However, if you don't want to do it, you can also avoid doing it. let's do this question without creating a general formula. I hope you have copied this. Should I go to the next page? Let me try it. Okay. So energy of fermions, what do we have, people? 2 E0, 6 E1, 7 E2. Okay. 2 E0, 6 E1, and 7 E2. So actually, the value of En for 3D people, remember for 3D, it is n plus 3 by 2 x squared omega. So this is 2 into 0 plus 3 by 2, that's 3 by 2. Okay. Then 1 plus 3 by 2, that's 5 by 2. And then you have got 2 plus 3 by 2, that's 7 by 2. Okay. So you can take this half x squared omega common, maybe, and half x squared omega common. You'll be left with 2 into 3 is 6, 6 into 5 is 30, 7 into 7 is 49. So we have got half x squared omega into 49 plus 30 is 79 plus 6, 85. Okay. 85 by 2 x squared omega. Answer is 85 by 2 x squared omega. But it depends in what terms they're asking. We have to take the ratio now. So we'll keep it like this. Let's keep it 85 by 2. Any questions? Anyone? Anywhere? Please ask. Don't hesitate. Okay.
Yes, sir.
Chalo. What about bosons? All the how many bosons are there? 15 bosons. All the 15 within the ground state. 15 E0. So 15 into ground state has 3 by 2 x squared omega. Okay. So 15 is 45. 45 by 2 x squared omega. Bosons is also there. What about spinless fermions? Okay. 15 now. Remember, B generality is 1, then D generality is 3, then 6, and then 10. Khatam na? 1 will be in the ground state. 3 will be in the first excited state. 6 will be in the second excited state. How many are remaining now? 6, 9, 10, 5 are remaining, right? So 5 will be in the third excited state. I hope you understood without drawing this time I concluded. Because I already know the D generality, why do you want to draw? If you want to draw, you can always draw. Like if we go on drawing the diagram, in that case, in 0, 0, 0 state, I have got only one fermion. Okay. Then in 0, 0, 1, 1, 0, 0, 0, 1, 0, 1 fermion, 1 fermion, 1 fermion. You still have 3 now. Similarly, you will have 6 here, and total are 15 now. So 6 is done, 3 is done, 1 is done. How many are remaining? 6, 9, and 10, 5 are remaining. So 5 will be here. 5 will be 3. Without drawing, you can directly guess. We have learned enough to directly jump down. Okay. Tell me if not. Otherwise, you can always solve right now. So what we have our answer this would be E0 plus E0 is 3 by 2 x squared omega plus 3 into 5 by 2 x squared omega. Okay. Plus 6 into 7 by 2 x squared omega plus 5 into 9 by 2 x squared omega. So let's take half x squared omega again common. We are left with 3 plus 5 3s are 15 plus 7 6s are 42 plus 5 9s are 45. So we have got half x squared omega into 45 plus 42, that's 87 plus 15, that's 102 plus 3, that's 105. Okay. So final answer is the ratio of fermions to bosons to spinless fermions. It is 85 by 2 x squared omega is to ratio to 45 by 2 x squared omega ratio 105 by 2 x squared omega. So people x squared omega by 2 x squared omega by 2 x squared omega by 2 gets cancelled. We have got 85, 45, 105. All of them goes in the table of 5. So this is 5, 13, no, 5 17s are. This is 5 9s are. This is 5 21s are. We have got 17 is to 9 is to 21. That's the answer. Nicely created. Ask me if you have any questions. So we will stop here for the evening. We'll continue with more questions related to boxes and harmonic oscillators combined together. We'll also take anisotropic harmonic oscillators tomorrow. And then we will start with the different well potentials that are remaining in the chapter. Thank you so much, everyone. You all really. That's about you have to go to the next page copy also. So just in case. Problem.
Thank you, sir.
No problem. No problem.
Thank you, sir.
Thank you, sir.
No problem. Something in the chat box. Thank you, sir. Harry, welcome. Take care. So I'll end the session, people. Tell me if anybody's right. See you tomorrow.